So what we're going to talk about in this section is how you graph any type of polynomial, no matter what kind of polynomial it is. The first section we talked about specifically quadratics, and those are degree 2 polynomials. And what we need to know is how you graph any type of polynomial, regardless of what degree it is. But before we do that, we want to make sure we understand a couple of things when we talk about polynomials. And I'm going to just make a kind of graph here to understand a few things. Anytime you are graphing a polynomial, it has to be a smooth graph. There are no breaks. So you might ask, well, what's an example of something that has a break? Well, an example of something that would have a break would be something like this. So polynomials can't have breaks in them. So when we're graphing things, know that everything's going to be a continuously drawn figure or graph. Another thing is that everything that we have is a smooth graph. So this is an example of a break. Everything is a smooth curve. Okay, so an example of something that's not a smooth curve would be an absolute value graph. Okay, this is an example of something that doesn't have a smooth curve because it has a sharp turn there at 0. So these two types of things are not examples of polynomials. So when we graph them, we're going to be talking specifically only about these types of things. It's smooth, doesn't have any breaks. So what we're first going to do is we're going to sketch a graph of any function. Now, before we talk about anything in relation to how we can use specific properties of this, I'm going to just do what we've learned before we graph anything, and that is to plot points. So I'm going to go to -3, -2, -1, 0, 1, 2, 3, and see what happens. So if I take -3, well, first of all, I'm going to use 0 because that's the quickest, because that's 0. If I plug 1 into that, we get 1 to the 5th, which is 1, but then the opposite of that is -1. So the point 1 comma -1 is on this graph. Then I go to 2, I do the exact same thing, 2 to the 5th power, and then the negative of that. Well, that's going to be, well, 2 to the 5th power would be 32. So you can already see that this is completely blowing up as I get bigger and bigger with this. And if I get to the next one, I'm going to get to -3 to the 5th power, which actually goes to -243. So there's no point in trying to graph this from such a large scale. And if I plug -1 in, since this is an odd function, it's going to behave so that it's a positive 1 for a opposite of -2 to the 5th. It's going to be a positive 32, and this is going to be a positive 243. So we have something here, then something way up here, and then it just completely gets out of control. So the way that this looks, if we draw a smooth curve, it goes extremely down very fast and extremely up very fast on the other side of the y-axis. So it looks completely new to us, but I'm going to show you how everything kind of comes together in a little bit. Now I'm going to look at this one over here and do the exact same thing, but you're going to find out very quickly that these numbers are going to explode on us very quickly. So if I pick 0, that's 0 plus 1 to the 4th, that's 1. If I plug in 1, that's 1 plus 1 to the 4th power, that would be 16. So you can see it already gets very out of hand very quickly with this one as well. If I plug in -1, I get 0. If I plug in -2, I get a -1 to the 4th power, which is a positive 1. And if I go one more, you're probably going to find that if I go to -3, It's going to be a negative 6 or a positive 16. So this gets out of hand very quickly. And you can see that this almost looks identical to a parabola. Okay? Now, if I had a graphing utility on the screen, you could see how they compared. And they look almost identical. But up to this point, we really don't have a whole lot to talk about in terms of how we can graph these except by plotting points. Okay? So when you first learn how to graph things, the first thing you do is you graph them by specific points. Now what I'm going to talk about is how specifically all graphs, at least polynomials, fall into a specific category. All right? Now you have to understand that a polynomial is written like this. Okay? And this is just fancy notation for saying that we have a list of coefficients all the way down to a constant term. So these right here are just ways for saying coefficients. And these are just exponents. Now there are certain things that are always going to be true regardless of what the function looks like. Regardless of what the function looks like, there's going to be certain properties that hold true based on a couple of things. First thing is the leading coefficient. Okay? The leading coefficient is when it's written in standard form, it's the very first number you see. All right? And there's going to be one thing that's going to happen for all of these. Or excuse me, there's going to be two things. Either the leading coefficient is going to be positive or it's going to be negative. And there's two cases where it's positive, there's two cases where it's negative. So the first thing you look at to tell what a general shape of the graph looks like is based off of the leading coefficient. The second thing is if you look at the degree. So if it's the highest exponent you see is a 2, then it's a degree 2. If it's 5, then it's a degree 5. These up here were a degree 5 and a degree 4. So the highest exponent you see, you're going to see two possible things. Your degree is going to be even or odd. So we have 4 different scenarios. Our leading coefficient is going to be positive or negative, and our degree of our function is going to be even or odd. Now, if our function has a leading coefficient that's positive and the degree is even, this is how the general shape of this graph is going to look. It's not going to be very specific, but we know that at some point in the graph, as x gets extremely negative, so x is going towards negative infinity. Okay? What that means is the numbers that you pick for x get smaller and smaller. What happens is that your y values, or f of x, goes up. So it's going up. So it's going towards a positive infinity. Okay? So as this function gets more and more negative, it's going up. The same thing is true as x goes towards positive infinity. All right? As x goes towards positive infinity, f of x is also going towards positive infinity. So the y value is also going towards positive infinity. So the graph is starting from a negative value going up, and from a positive value, if you increase it, it goes up as well. Okay? The rest of this is going to differ for all sorts of graphs. It could look like this, for all we know. And then this is a smooth part right here. It could look like that. There could be about 10 different turns here. all that is important are these two things. And this is very hard to kind of grasp without seeing some examples to know what it looks like. Okay? But having this down will be important to see for any graph that you see. Now, when it's odd, but your leading coefficient's still positive, the end result of your graph is still going to be exactly the same. So when x goes to infinity, your function goes to negative or positive infinity. The difference is that when you deal with an odd function, it goes down. So when x goes to negative infinity, your function has a tendency to go towards negative infinity as well. What that means is as you go left on the graph, your graph is going to go farther and farther down. It doesn't matter what the rest of this looks like. We're going to talk about how you fill that in, but it could look like this. It might not even have one turn at all. It could look just like a line, because a line is a degree 1 function. But that is the general shape, and these two parts right here are the important parts. If the leading coefficient is negative, but the degree is even, it's almost identical to this except it's reflected. So as you get negative, it's going down. As you get positive, it's going down. So when x goes to positive or negative infinity, doesn't matter which one, your function is going towards negative infinity. So the rest doesn't matter. It can be just a parabola. And that's what it looks like. There could be some different variations for this as well. Okay? Now, if the leading coefficient is negative and it's odd, it's the mirror image of this. So it starts positive in a positive direction, and it's got to finish at some point in a negative direction. So as x goes to negative infinity, the function is going towards positive infinity. And as x goes to infinity, f of x goes to negative infinity. Kind of ran out of room there. The rest doesn't matter. It can just be a straight little curve and a line, and that's your function. So these are important to know because these are what are called end behaviors. It tells us how a function behaves at the end as you get extremely large or extremely small values. Okay? So what we're going to do first is we're going to label these and talk about specifically what we know. Okay? So for this, we know that since it's written in standard form, in descending powers, the leading coefficient is negative. And we know it is an odd degree function because it has a third power. That's a third degree function. This one here is a even degree, and it has a leading coefficient that's positive. This one is a function with a leading coefficient that's positive, and it is odd. So we have these labeled. I'm going to do something a little bit more to talk about this, but before I do that, I need to talk about the next example so we can talk about something a little bit more. We're going to talk about how you find zeros, and then we're going to tie that back in so I can get a little bit more specific graph for each one of these functions. So we're going to talk in the next part of the video about how you find zeros of a function.